Okay, today we have to discuss the electric field produced by a charged ring, and this is a ring which is given, we uniformly say positively or positive charge, right? For this charged ring, we want to find the electric field at this point P, right? So this is the radius of that ring, and OP, the distance of that point from the center of the ring, is R. Now this distance will be the hypotenuse of the triangle OP and Q, that will be equal to R square plus A square of under root. Now imagine a very small part of that ring whose length is dl, right? And this dl segment will have very small quantity of charge in it. First we shall find that charge contained by this small segment. Okay, for that, first suppose Q is the total charge given to the ring, where A is the length of the ring, then charge per unit length is equal to what? Total charge over total length of that wire or this closed wire called ring. So lambda is called linear charge density, as we studied in the last topic. Lambda is equal to the total charge given to the body over its circumference, that is 2 pi and A, right? This is linear charge density. Now come back to this segment. This is a small piece of that charged ring whose length is dl. So the charge contained in this small segment is dq. So dq is equal to, that is charge on dl line element. dl line element, that is dq, is equal to its linear charge density multiplied by the length of that particular segment. So lambda is equal to, we have q upon 2 pi a into of dl. Okay, so far things are quite easy. Now we have to come to the section of figure. This segment dq having charge dq, suppose this is a very point charge, a small point charge placed at position, this having a distance of again equal to this. So this small region will produce electric field at this point, that will be directing along this line. Clear? That will be directing along this line. So the field produced by this small segment is equal to pointing to this direction, that will be a small electric field dE. If I extend this line OP, as I already suppose this is angle theta, so this must be angle theta, because from the figure it is clear. So this angle again equal to theta. Now this dE, which is a vector quantity, it will have its one component along the axis of the ring, that is given by d of E cos theta, and that is called axial component or horizontal component, and its vertical component will be perpendicular to this axis, and it is given by this equal to dE sin theta. Okay, this is the splitting of the component of electric field in horizontal and in vertical segment. Now come back to one more point, that is diametrically opposite point of this segment. obviously its diametrically opposite point will be here. This is another small element of length dl which have a charge of dq again. So this component will again produce a field along this line. So extend this line. This is again equal to d of e, because we have chosen the two line elements equal to each other. So they have carrying same amount of charge. So they will have same intensity of field producing at that point. Now again split its component into horizontal and vertical component. Remember, this one arrow is for the horizontal component of this electric field. Now I am using a red arrow which is the horizontal component of this electric field, that will be again equal to dE cos theta, right? So colors are for different components produced by the different parts. Again, its vertical component will be equal to pointing downward, and it is equal to dE of sin theta. The figure is now complete, and we have to use some analysis over here. That is, this dE sin theta and this dE sin theta both are equal and opposite in magnitude and direction. So they must cancel each other. It means the net electric field will be produced only by what? The horizontal component, dE cos theta and dE cos theta, right? It means the vertical components simply cancel each other. What we have to focus on, that is horizontal component. So we have a large number of diametrically opposite points producing dE cos theta over here, which are along the same direction, that is along the axis of the ring. And so their field will be added vectorially, and the horizontal vertical component becoming equal and opposite, they cancel each other. But that is simple. So the total electric field can be obtained by integrating the horizontal component. So we must write something. The perpendicular components cancel each other, and the horizontal components add up, are added together. Okay. Now the total electric field will be given by the integration of this small horizontal component. That is, the total electric field E is equal to integration of dE cos theta, right? And when the limit goes to what? The length of the ring starts from 0 and it ends up to 2 pi and A. Now put all the values. First, what is the dE? Before doing that, we shall write what is the value of dE. dE is equal to 1 upon 4 pi epsilon naught dq upon this square of this distance, and it is equal to, suppose, or this is equal to, both are same, tp, okay, tp square, and its direction will be along that way as given by the, so this is our notation for the direction. Now what is equal to dq? dq is equal to lambda dl, or this. So we have 1 upon 4 pi epsilon naught, the total charge, upon 2 pi a, and that is dl over t of p whole square and t of p vector. Clear? Now we shall put this quantity in here, and cos theta from this triangle, find the value of cos theta again. So cos theta is equal to base upon hypotenuse. What is base? Here is it r, and here it is r square plus a square to the power half. Clear? That's the simple value of cos theta. Now put all the values and get integration. So 1 upon 4 pi epsilon naught will be out of the integration. Q will be out of integration. 2 pi a will be out of integration. That is Q 2 pi a. Remember, for this particular point, the value of this distance does not change. It means Tp square should be come out of the integration. That is T of P square. What is left alone? That is dl. dl, and again the value of cos theta is equal to r square upon this. So this is r over r square plus a square to the power half and integration putting over here. Now again we see that this quantity is a constant again. So take this again out. So we are here, that is E equal to 1 upon 4 pi epsilon naught Q, and this R goes out, Q R, this as well go out, 2 pi A. Now what is Tp equals to? Tp means this length means square of this, so this is equal to R square plus A square, right? And this quantity again coming out, so R square plus A square to the power half integration of dl. Rest of the things came out of the integration. Now whose limit is 0 to 2 pi a, 0 to 2 pi a. Now solving this quantity, 1 over 4 pi epsilon naught q r 2 pi a r square a square 3 by 2. The value of this quantity is, we are simply adding all the small elements along the ring. So this equal to the total length of that ring, that is equal to the perimeter or circumference, that is 2 pi a. Simply that is 2 pi and a, right? So this is 1 upon 4 pi epsilon naught 2 pi a q r upon r square. Okay, before that I think this should be cut. This is gone. Q r upon r square plus a square to the power 3 by 2, and that is the net magnitude of the electric field at a distance r from the center of a ring of radius a, okay, at a point P. So this is what this value gives the total electric field at point P due to this charged ring, right? Now what if we have two cases? If the r becomes very large, or if r becomes 0, then two cases will be. Case number 1, when r is very greater than a. In that case we shall neglect the a square and we are left with E equals to Q R 1 upon 4 pi epsilon naught r square to the power 3 by 2. Okay, so this cancels 2 and we are left with r to the power 3. So one more power will be cancelled by this r. So this 3 remains 2. That is Q upon 4 pi epsilon naught r square. Now this is the electric field produced by this charged ring when we are talking about a distance which is large enough compared to that of the radius. Or in other words, we find that this is the same result as we obtained in case of a point charge. It means this result is exactly like that of a field produced by a point charge at distance small r from itself. So what is the outcome of this case? It means if this case is to be hold, then the whole charge ring for that particular point behaves like a point charge. Rather we say, it is suppose that the whole charge on the body is finally concentrated at this particular point. That's it. This is the same result. Now, what if this A is very large and compared to this R? Then we have a different situation, that is A is far greater than R, then E is equal to 1 upon 4 pi epsilon naught Q R square. Can we remove this? Yes, that is A square to the power 3 by 2, or E is equal to Q R upon 4 pi epsilon naught, and this 2 cancels 2, so A to the power 3. This is the final result when the size of the ring is very large compared to that of the distance between the point from its center. Okay, so please note down this, and if you have any doubt, please write me.